let me introduce our next talk and our next speaker. His name is Andrea Continella. He is an assistant professor and postdoc at University of Twente in the Netherlands. Of course, he is Italian. He comes from Sicily. Previously, he was a postdoc researcher in the computer science department at the UC Santa Barbara, and he obtained a PhD cum laude in computer science engineering at the Politecnico di Milano. So his research activity focused on security, system security, malware analysis, mobile IoT security, privacy, automated vulnerability discovery, as we will see in this next talk, and large-scale measurement of security issues. So he published several research papers, academic papers, and serves the program committees of well-known system security conference and workshops. So he is also organizer of some CTFs and participant to some CTFs. He is part of a Shellfish team and co-organize some CTFs like Poly CTF and ICTF. His next talk is about identifying multi-binary vulnerability embedded in firmware at scale. So the focus is specifically on embedded devices, IoT devices, and basically low-power, single-purpose embedded devices. Okay, that have become ubiquitous. We know of recent larger-scale attacks, for example, the Mirai botnet and similar botnets performing DDoS larger-scale attacks, so with these, the analysis of the malwares that have become extremely common and extremely valuable in the cybercrime underground is quite complex. So it's very hardware dependent because it uses minimal environment with custom hardware components, and moreover, they often use a model of based on multiple binaries. So these approach and these tools that Andrea will present, Karonte, that is the result of a very interesting research they did, is suggesting and is implementing a new approach in the analysis of these multi-binary firmwares, and especially applying a kind of a taint analysis approach on the multi-binary firmware of embedded devices. So I won't add anything else apart that with this kind of approach, they identify several 0 days in several embedded devices, and some of them are really valuable with remote code execution and CVSS above 9.6. And I will leave the stage to Andrea in a few seconds. Bye.
Hello everyone, thank you for virtually attending my talk. I'm very happy to be part of this second edition of No Head, even if unfortunately not in person. My name is Andrea Continella. I'm an assistant professor at the University of Twente in the Netherlands, and today I'll talk about a research project on automated firmware analysis in collaboration with some folks at UCSB. So first of all, why do we want to analyze firmware? Well, I'm sure you noticed that IoT devices are nowadays quite popular. I would say they're everywhere, and there exists a very large amount of different devices, right? So we have smart toasters, smart lights, smart bulbs, and now we also have a smart egg minder. It's not clear to me what this is supposed to do, but anyways, the common thing is that we have seen all of these devices often being vulnerable, and not only they contain indeed security vulnerabilities, but we have seen such vulnerabilities being actively exploited by attackers in the wild. And the most famous example is probably the Mirai botnet, where thousands of IoT devices were compromised to perform a large distributed denial of service attack. Now, one interesting aspect in this scenario is that often the vulnerabilities that we find in these devices are quite old types of vulnerabilities, or things that we have known for a long time and for which attackers do not really need advanced, sophisticated exploitation techniques. And in fact, firmware often does not present many of the protection mechanisms that we are used to in modern operating systems. And here I'm thinking, for instance, at randomization or control for integrity and so on. But at the same time, firmware presents some significant differences when compared to, for instance, desktop applications that make traditional security analysis hard to apply. And the main reasons are, first of all, that firmware is heavily hardware dependent. So it relies on many peripherals. Just think about a smart camera where the firmware is programmed to directly talk to the camera sensor to retrieve images. But also firmware lives in unique, minimal and execution environments with non-standard configurations. So for instance, shared memory, hard-coded addresses, but also custom interrupt enders that can be implemented within the firmware image. And on top of this, of course, there are several architectures, sometimes also proprietary ones. These things make things a little bit tricky to implement. So if we want to analyze a firmware image, what we can do, first of all, we can try with dynamic analysis, right? So imagine that we can emulate our firmware image and we can run our coverage guided fuzzer. Well, unfortunately, this is not very generic and reliable at this time. There have been recently some very promising works on this direction, but we're simply not there yet. And the reasons are, again, that mostly because firmware is heavily hardware dependent. So properly modeling and implementing dynamic analysis environment for firmware is challenging. This is because this environment has to model and implement peripherals, DMAs, interrupt enders, and so on. So all these things are quite tricky to deal with. The alternative, of course, is that we could instead use static analysis, which does not suffer from many of these limitations. But here the problem is that current approaches do not scale and generate too many false positives. And the reason for this that we found in our research is that firmware is mostly multi-binary. In fact, the vast majority of firmware images are Linux-based, and in practice they consist in a squash file system that contains hundreds of executable binaries. You can see an example here of a firmware image that contains 240 binary programs, but on a larger scale we found that on average a firmware sample contains more than 150 executable binaries. Of course, not all these binaries are indeed used and needed to implement the firmware's functionality, but some of them do. And the typical architecture of an embedded system consists in a binary in a program, usually a web server, that receives requests and forwards the request to an handler binary. The handler binary processes the request and then returns a result. In practice, this is a little bit more complex because we can have multiple handler binaries, and these binaries can further interact with other programs. So at this point, the question becomes which binary we want to analyze, because clearly on the one hand, if we only select a random number of binaries or we only focus, for instance, on the web server, we might miss a large amount of vulnerability. So we might have many false negatives. But on the other hand, if we analyze all these binaries individually, then we will have a large amount of false positives. And so you can see an example here. This is from a real-world firmware image where we have the corresponding source code of a binary program on the right, and this program receives and reads data from two environment variables. If you assume that this is the input of the program and this is attacker control, then this program contains two vulnerabilities, because this data, this input, is used in two unsafe string copy that do not check, without any check on the size of the destination buffer. So these are two buffer overflows, easy, two bugs. In reality, in this specific firmware image, this program on the right is only executed through this other program on the left. And you can see here that this other program sets the values of these two environment variables and then execute the program on the right. So now, if we look at the big picture and we consider the interaction between these two binaries, in this case, we only have one bug. In fact, while the value of the query string variable can potentially be longer than 128 bytes, so longer than the size of the destination buffer, the log path variable is hard-coded and constrained to a string that is shorter than the destination buffer size. So in this case, not generating any buffer overflow. And this is, again, a quick example, but of a false positive that occurs when we look at binaries individually. But you can imagine how the number of false positives can quickly increase if we look at many binaries and we want to analyze many firmware images at scale. So during our research, we started from the observation that firmware is mostly composed of multiple interacting binaries, and we found out that modeling the interactions between these binaries is essential for an effective analysis. We can model those interactions because programs and processes communicate through a finite set of channels, a finite set of inter-process communication paradigms. Modeling these interactions, we introduce static analysis techniques to perform multi-binary taint analysis. So multi-binary taint analysis where the constraints of our taint analysis are not only propagated within one single binary, but they are also propagated from one binary to another. On top of this approach, we built a prototype, Karonte, and I'll show you in this presentation that Karonte can discover unknown bugs, but at the same time, it can drastically reduce the number of false positives. So in a nutshell, if you want to quickly summarize what Karonte does, it takes as input a firmware image, it unpacks the firmware image, extracting all the existing binary programs, and then it detects what we call the border binaries. So these are the binaries that accept user input from the outside world. Once we have these border binaries, Karonte tracks the interaction with additional programs. You can see here an example, two programs that share data through an environment variable. And what happens in practice is that these two programs know the name of the environment variable that we call the data key of the communication, in this case the string value, and by knowing this data key they can actually share data. And of course all of these binaries, all these programs can then interact and communicate with additional programs. Now Karonte has what we call a binary dependency graph, so this graph that connects all the programs that communicate, and we can run our multi-binary taint analysis. So we start collecting constraints on the tainted data, and in this case, in this example, we can see that these programs share data that is supposed to be up to 512 bytes, but when this data reaches the very last binary of this chain, it is copied into a buffer that is only 500 bytes. So in this case, leading to a buffer overflow. So now things are probably not super clear. So let's have a closer look at the different steps that Karonte performs. So the first step, as we said, is unpacking the firmware image. So we use binwalk to unpack the firmware images. And once we have extracted all the binary programs, we want to automatically identify the border binaries. So those programs that accept user input. The intuition here to do so is that these programs will need to parse user data, so they need parsers. And there exist in the state-of-the-art techniques that allow to identify parsers in binary programs. We extended these techniques by specifically focusing on network parsers. And so what we do to identify these binaries is that for each function in all of the binaries contained in a firmware image, we compute a set of features. We compute the number of basic blocks, the number of memory comparisons, the number of branches, the number of network-related keywords, and also we check whether there is any data flow between a receive function and a memory comparison. All these features produce numerical values that we sum up together using this formula with some constants and weights. But what happens here is that for each function we get a score. And then we select as the score of each binary the highest score of its functions. So now we have for each binary a parsing score, and we want to identify border binaries, so we use machine learning, specifically clustering, to identify those binaries. If you're not familiar with machine learning, imagine that given the distribution of the different parsing score, we automatically select the group of binaries that present a significantly higher score than all the other binaries. Cool, now we have our border binaries, and the next step is that we want to identify interactions with other binaries so that we can build our binary dependency graph. To do so, we use a static taint engine, and we start by tainting data compared against net-related keywords. The assumption here is that this is the input of our firmware. And we also manually created a list of net-related keywords that we use for this step. Then we start the taint exploration, and we rely on some modules that we call CPFs, communication paradigm finders, that reason about the different inter-process communication paradigms. So for instance, we have a specific module for identifying socket-based communication, another module for identifying file-based communication, and so on. And so whenever for each basic block that we analyze during our taint exploration, these CPF modules identify whether there is any data being shared, and if it is so, they perform three tasks. They first of all recover the data key of the communication. Then the second step is to determine the flow direction, so whether the binary that we are analyzing is actually sending or receiving data. And finally, in the case the binary is sending data, we want to find all the other binaries in our firmware image that, using the same data key, receive data. So we can see this again in an example. So here we have a comparison against network related keywords. So in this case, the string SOAP is our keyword. And so in this case, we consider P, the buffer P, as our input, so P is tainted. What happens is that this buffer is then returned by the parse URI function, and so also the buffer data is tainted now. And this buffer is later used in a setenv. So here our CPF identifies that there is some data being shared. It extracts the data key, so that the query string value, and it looks for other binaries that receive data using the same data key. And we can see here on the right, the receiving binary that using the same data key query string receives data from the environment variable. Whenever this happens, or whenever we find these communications, we basically produce an edge in our binary dependency graph that connects these two binaries. When we do this for all the binaries contained in our image, we have our fully built binary dependency graph. We can start our multi-binary data flow analysis. So in this step, we track how data is propagated from one binary to another, and we collect constraints, the constraints that each binary applies to the tainted data. We implemented this on top of Anger, a popular binary analysis framework that also implements symbolic execution. And you can imagine here that one of the big steps, the big problem here is that when we do so, we should consider all the possible paths in a program that apply constraints to our tainted data. This is of course unfeasible, so what we do is that we explore paths within a certain time limit, and we propagate only the least strict set of constraints to the next binaries. Why the least strict set? Because we are looking for vulnerabilities, and under constrained data is more likely to lead to security vulnerabilities. So let's come back to our example. In this case, this is the location where data is being shared. And if we go back, this data can be produced by two different paths. The difference between these two paths is that in the second case, the data is constrained and can be up to 127 bytes, while in the first path there is no constraint at all, so that the size of the buffer P is not specified, is unlimited potentially. So in this case, since we want to look for vulnerabilities, what we do is that we select the least strict set of constraints. So in this case, we go for the first path, and in the binary on the right, we set the query buffer to be unconstrained. Okay, nice. Now the last step of our approach, while we do our data flow analysis, we want to uncover vulnerabilities. So the type of vulnerabilities that we look for are buffer overflows and denial of service vulnerabilities, specifically attacker control loops. And what Karonte does to do so is that, of course, we taint data sent and propagated from one binary to another, and Karonte raises an alert whenever tainted and under constrained data reaches async. What's async for us? Async is a memcopy-like function, so any function that is semantically equivalent to a function that copies data from one source to a destination, but also a difference of tainted variable and a comparison of tainted variables in loop condition. If we go back again to our example, we can see here that this is the location where this binary receives tainted data, and this data is later used in the process request, and after some processing it reaches a sync. So there is an unsafe string copy here without any check on the destination sides, on the size of the destination buffer. So in this case, Karonte produces an alert. Cool, this is our approach. To show that this really works in practice, we first of all performed a in-depth evaluation, and in this case we analyzed 53 firmware images from 7 different vendors. We actually found 46 new 0 days. We got a bunch of CVEs, but not only Karonte was able to detect these unknown bugs, but it was able to decrease the number of alerts, the average number of alerts, from more than 900 to 5 alerts per firmware image. This is an alert reduction of 2 orders of magnitude, but at the same time keeping a very low false positive and false negative rates. So we can see some numbers about this reduction in this table. These are some statistics about the number of binaries, the number of alerts, and the execution time required to analyze these firmware images when using traditional static analysis approaches. So when dealing with each binary individually. Here on the right, instead, you can see the same numbers when we apply Karonte's approach. And you can see that there is a quite significant reduction both in terms of number of alerts, but also execution time required for analyzing this firmware image. We also perform a larger scale evaluation. So in this case, we collected almost 900 firmware samples. We found that almost 40% of them contain multi-binary interactions. And we also manually inspected 100 alerts out of the 1003 alerts that Karonte generated during this analysis. We found that 44 were actually true positives, and 30 of these 44 true positives were actually multi-binary vulnerabilities. So just to give you a bit more insights about our analysis, this is the distribution of the size of the binary dependency graphs in our evaluation. So you can see that the vast majority of firmware images produces BDGs with 5 binaries that interact with each other, but we also see quite complex BDGs. For instance, there was one sample that produced a binary dependency graph containing 16 binaries, which was quite surprising for us, I would say. Perfect. Then in terms of execution time, Karonte indeed takes a bit of time to analyze a firmware image, on average 15 hours. But the good thing is that this time scales well when the size and the complexity of the firmware image increases. You can see in these two charts on the right, and you can also see in these charts there are some spikes. This was actually due to implementation issues, specifically because Karonte is still using, unfortunately, an older version of Anger that was not optimized and was taking a lot of time to compute some control flow graphs. This is now way faster in the latest version of Anger, and we will hopefully soon update our prototype of Karonte. So now you've seen, you know how Karonte works. Let's see how to run it. So we released all our code on GitHub. You can see, you can find it at this URL. And in the same repository, you'll find instructions on how to download a Docker image that comes with Karonte already installed and ready to be fired. And if we look at this Docker image, you can see you can find here some folders and our code. And to actually run the tool, you need to create a configuration file. So we have some examples here. This is, for instance, a configuration file for a specific firmware image. You can find on our repository all the instructions on how to what all these settings means and how to use them. But then if you want to run the tool, you actually need to only pass this configuration file in the command line. So if I run this command, now we should have Karonte running on this specific firmware image. As I mentioned, this will take quite a bit of time, so we'll not wait for this to finish, but I want to show you what happens when this terminates. So at the end of the analysis, Karonte produces a log file. You can see this here with all the information about the analysis. But instead of looking at this text-based log file, we recently implemented a very simple UI to visualize these results. And if I run this command, nothing really fancy, but we should be able to see some information about this firmware image and this specific analysis. So we can see that this image contains 128 binaries. Luckily, not all of them process user input, so we can see actually a rather simple binary dependency graph. The light dots are the border binaries. We can see additional information about, for instance, like the data keys that are used in the communication between different binaries. But the nice thing is that we can actually look at the alerts generated by Karonte. So if I select the first alert, we can see that the path of this alert is highlighted in this graph. And this is specifically an alert produced by a data flow which started in the HTTPD binary that communicates with the fileaccess.cgi binary. This communication happens over a content type data key. This is the address of the buffer used to share data, and this is the address of our sink. So this is where our data flow ends up. So this is where potentially we might find a vulnerability. And indeed, we combine this with Anger's decompiler. So if I click on the very last binary of this path, Anger is going to decompile the potentially vulnerable function. The decompiler in Anger is still a work in progress, so you'll see that the decompiled code is not, the quality is not great, but it's still good enough for us to spot a real-world vulnerability. So you can see that in this function, this program receives tainted data from an environment variable, and later on, believe me, this data is used in an unsafe string copy, so leading to a buffer overflow. This was a quick example, but this was indeed a real-world vulnerability, and of course we disclosed this vulnerability and everything else that we found to the responsible vendors, many of which are already released patches for their devices. So to wrap up this presentation, a brief recap of what we achieved. We introduced static analysis techniques to perform multi-binary taint analysis, and our prototype Karonte is indeed able to discover unknown bugs in embedded firmware by drastically reducing the number of false positives. an interesting aspect of our research is that despite program analysis is quite a complex task, even when applied to a single binary, scaling program analysis and binary analysis to a multi-binary environment is possible because modeling the interactions between these binaries can make things quite easier. Perfect, and thank you for attending this talk. Just a reminder, there is an academic paper on this, so feel free to check it out if you want to read more details. And then I'll be happy to take any question on the live stream. Ciao.
Hello, Andrea.
Hello. Hi.
Hello, how are you?
Good. How are you?
Also good. So that was an amazing work. So
Thank you.
as you can see from the Q&A data, it raises some attention and some questions. So let's start from the first question. It's by Sukhdev. He wrote, "What happens when someone like Filippo Cremonese tries to manually and maliciously patch the binary file?"
Yeah, that's a great question. And first of all, I hope that Filippo can patch all our firmware so that we have more secure devices. That's of course the end goal of our research, right? So we want to identify vulnerabilities because we want to patch them and make these devices more secure. And patching is also something that we are working on. The tricky thing is that applying techniques like the ones that Filippo described really nicely in the firmware domain is a little bit more complex because firmware presents some characteristics that make this analysis particularly difficult to apply. And I can give two examples, for instance. One is that firmware images are usually flashed into memories that have very small and fixed size, right? So it's often not possible to inject and add additional code in a firmware image. So if we want to patch something by introducing and injecting new code, we have to replace something that is already in the firmware image. We don't have any space left. This is very common. And the other thing is that firmware images often present integrity checks to avoid tampering. If you modify and change anything in the firmware image, then the signature check or the integrity check will be destroyed basically, and so the firmware will not run. So this is another challenge that when you want to patch firmware, you have to deal with this. You have to somehow adjust also these checks.
Okay, nice. So the second question is, did you evaluate the false negative rate based on known vulnerabilities? So you mentioned that this was proven very effective and quite accurate, but and you show some numbers about the false positive, but probably the question is on false negative.
Yeah, that's also another great question. We did it for the let's say small scale experiments, or where only when looking at the 53 firmware images, not in the large scale scenario, because that would be a little bit say more difficult to do. What we did is that we look for CVEs, non-CVEs for the same firmware images, and we found that the vast majority of them were covered by our approach. We did find some false negatives. I remember two for sure, and these were due to the fact that the binaries were presenting some weird ways to address and reference to strings. If I remember correctly, one of them was computing the address of a string by computing an offset from the global offset table. But there were some things that Enger, our underlying analysis, was not able to properly track down. And so we missed some strings, and this resulted in us in failing to identify the border binaries, which is the, let's say, the initial part of our approach. And so this made the analysis fail. What we did is that to check that this was still, let's say, the later part of our analysis was still working, we manually added these binaries as border binaries, and then Karonte was able to detect the vulnerabilities later on. But indeed, there are of course, some limitations.
Yes. And then the next question is, did you test any enterprise-grade network or security appliances? Do you see any, in case you didn't, do you see any limitation in using this approach on stuff like client VPNs, load balancers, etc., for which we saw a spike in disclosed vulnerabilities recently?
We did not test any of these security appliances. On a, let's say, on a high level, I don't see any specific limitations that could prevent this approach to be applied. There might be some, engineering or technical difference that we might need to implement in the case these appliances present some differences. But on the high level, I would say that this can be applied even in these scenarios.
Okay, thank you. And so we look forward to have a huge number of CVEs coming from something like this, no?
Yes, but also I would say also a very number of a high number of patches, right? So we want to find vulnerabilities, but we want also to patch those vulnerabilities. And patching in the IoT domain is particularly tricky. I mentioned already some challenges, but also in terms of deployment, right? Because sometimes also deploying patches for IoT devices or smart embedded devices, it's a little bit more complex. And so, yeah, the goal is to find these vulnerabilities, but also hopefully to make sure that those are patched timely.
Nice. So some compliments from Vinci and from Protozoo. How much time and effort was required to develop Karonte?
That's a nice question. I think in terms of development, it was about a year or maybe I would say around a year. But maybe many of these techniques are based also on Anger, which is this binary analysis framework that has been developed at UCSB. And so these also results of many years of research, right? So Anger has been developed and increasingly being improved over the past 5 or more years. So specifically for Karonte, 1 year, but also we use many of the results from previous research.
Nice. Okay. So thank you very much for your participation, and thank you very much for this amazing job. We have arrived at our first break, so have a nice lunch. I don't know what you are going to eat in the Netherlands. Something Italian, I hope.
Yeah, of course, something Italian. I think there's some nice pasta will be the easy solution for this.